Going to discuss about the structure and properties of alkanes. Properties of alkanes. First of all, it is said that alkanes are saturated hydrocarbons. That means alkanes has the maximum number of hydrogen that can be there with a carbon atom bonded to another atom, right? So we will compare an alkane and alkene. Alkenes have double bonds between carbon and carbon, and alkanes have only single bonds between carbon. So here, maximum number of hydrogen that can be there for a bonded carbon is 3, right? Like this, 3 carbon can be there as a maximum number. But for this alkene, only 2 hydrogen atoms can be bonded. So here, in this case, maximum number of hydrogen is taken by the carbon atoms, so that is saturated with hydrogen. So it is said that alkanes are saturated hydrocarbons. And then they are non-polar or very weakly polar. Alkane is a hydrocarbon. So in a hydrocarbon, in most of the cases, hydrogen and carbon and carbon bonds are there. Hydrogen has electronegativity value of 2.1 and carbon has 2.5. So here 2.5, 2.5. The electronegativity difference is 0. In here 0.4. Right? So here you can see the polarity of this situation is non-polar, and in such a situation very weakly polar, right? There are situations where carbon binds to other atoms in alkanes also. In such situations also they are very weakly polar or non-polar, right? As they are very weakly polar or non-polar, the secondary interaction between them is London forces. That means like this. There's a carbon atom. I'm going to draw methane here. A methane molecule joins with another methane molecule by London forces or dispersion forces. There are interactions between methane and methane. This is London forces or dispersion forces. The secondary interaction in the alkenes is London forces. In unbranched alkanes, first few members are gases at room temperature, and higher alkanes are liquids and solids. So if we compare the difference between gases, liquids and solids, the particles, interaction between the particles in gases is very low, and when it comes to liquids, somewhat harder interactions than gases, and in solids there are more and more attractions between the particles. So the reason behind this is the London forces. London forces depend on two things. London forces depend on surface area and molar mass. So if we think about an unbranched alkane, when the alkane's carbon number increases, the surface area of the alkane increases. For example, CH4 methane has a surface area like this, and ethane has 2 carbon, and due to that the surface area of it is higher. So when the surface area increases, number of London forces increases, so that the boiling points and the melting points increases. First few members have least number of carbon, and when going to higher alkenes, the carbon number increases, so that the surface area increases. Due to that, number of London forces increases and melting points and boiling points increases, making that the reason first few members of alkanes are gases at room temperature, for example methane, and higher alkanes are liquids and solids, for example nonane is a liquid at room temperature. When surface area increases, number of London forces increases, so that melting and boiling points increases with increasing carbon number. Is little bit different branched branched hydrocarbons. So we said that London forces depend on molar mass and surface area. Here there are two alkanes. These are branched alkanes. So here first alkane shown is 1-methyl butane, and second carbon shown is 2,2-dimethyl propane. So here you can see the carbon number is same. Here carbon number is same. Each alkane has 5 carbon and the molar masses are equal. You can see the molar mass of them are equal. So the factor to compare in London forces is surface area. Here this molecule has a larger surface area than this molecule. So when the surface area increases, we know that number of London forces increases, so that boiling and melting points increases. So when we compare these two, this has higher boiling point and melting point than this molecule's boiling point and melting point. What is the reason behind it? Surface area of this 1-methyl butane is higher than 2,2-dimethyl propane given here. Branched alkenes, even though molar masses is equal, surface area varies. When the surface area is higher, number of London forces increases, so that boiling points and melting points increases. Then we will discuss about the structure of alkanes. In alkanes, there are only single bonds between carbon and every other atom. Right? The simplest alkane is methane. 1 carbon and 4 hydrogen. The simplest alkane is methane. It contains a single carbon atom. Single carbon atom. Right? Then here CH4, C2H6, C3H8, that means methane, ethane, propane. These differ only by a CH2 unit. That means we'll see that CH4 plus CH2 is equal to C2H6. C2H6 plus CH2 equal C3H8. So here you can see these alkanes differ only by a CH2 unit, right? Such a series of compounds which differs only by a CH2 unit is known as homologous. Such series is known as homologous series, right? a series of compounds with similar chemical properties which share the same general formula, in which consecutive members of a series of compounds differ only by a CH2 unit, is known as a homologous series of compounds. General formula of alkanes is CnH2n plus 2. We will see whether it is correct. Methane is CH4. So we will put this into this formula. C N value is 1. So H value should be 2 into 1 plus 2. That means 4. So here H number has become 4 and carbon number is 1. So the general formula of alkanes is CnH2n plus 2. But cyclic alkanes doesn't follow this formula. You should remember that. Cyclic alkanes doesn't have this formula. Every carbon forms 4 covalent bonds with 4 atoms. Carbon has a valency 4, so it forms 4 covalent bonds with 4 atoms. So the number of VSEPR units is 4. We can calculate the number of VSEPR units by bond pairs plus lone pairs. So carbon has 4 bond pairs. So the number of VSEPR units of carbon in alkanes is 4. So due to that, the electron pair geometry and molecular geometry is tetrahedral. It is tetrahedral. You can see it in this diagram. I have drawn that. Here you can see tetrahedral. Form carbon-carbon single bonds. sp3 hybridized orbitals are linearly overlapped. That means the VSEPR of carbon in alkanes is 4. So the hybridization of carbon is sp3. Right? So the carbon-carbon bond is formed by the linear overlap of sp3 hybridized orbitals. And carbon-hydrogen bonds are formed by sp3 hybridized carbon orbital and 1s orbital of hydrogen. So here only sigma bonds are present within this alkane. So linear overlapping of sp3 hybridized orbitals and 1s hydrogen orbitals results in these 4 bonds. So we know that the electron pair geometry and molecular geometry is tetrahedral. So the angle between these bond is 109.5. Thank you for being till the end. We will meet in the next video.